Hi everybody, so this is going to be the video for Unit 1, Lesson 12, which is all about the intermediate value theorem. Now, throughout calculus, we're actually going to be learning several different theorems, and this is the first that we're going to cover. There are several learning targets for today. The first one is I can state the conditions and the conclusion of the intermediate value theorem. So we need to know what conditions we need to have in order to apply the theorem, and we needed to know what conclusions we are allowed to draw using this theorem. We need to be able to identify key words in a problem that indicate the intermediate value theorem must be applied. So we're going to be looking at how can we tell that we need to use the intermediate value theorem when we look at a question. We also have I can determine whether a function satisfies the conditions that are necessary for applying the intermediate value theorem. So once we know what the conditions are, do we know if a function satisfies those conditions? And the next one is I can apply the intermediate value theorem to answer questions about the behavior of a function over a given interval. So once we know what the conditions and conclusion are, and we know that we need to use the theorem, and we determine whether it's possible to use the theorem, we need to actually be able to do the problem. So I can actually do the application, apply this to a problem. And finally, and this is the really kind of trickiest one, is I can construct a complete justification referencing the conditions of the intermediate value theorem. So what we're going to use this theorem for is to justify why we know that certain things are true about a function, and that means we need to word our answer in a very specific way in order to completely justify our reasoning. Now I'm actually going to make this video in two parts. So the first part of the video is going to be an introduction to the theorem and going through what the theorem actually says. The second video about this topic will be doing some practice problems where we actually apply the theorem. So even though this is one set of notes, I'm actually going to break this up into two videos. So the first video is really about the introduction to the theorem. So let's go through this introduction. Imagine you're driving a car. While you are driving, you glance down at your speedometer twice. The first time you look, you note that your speed is 20 miles per hour. On your second glance, you note that your speed is 40 miles per hour, as shown in the pictures below. So we're going from 20, and then the next time we look, we're going 40. What is one speed that you can guarantee with 100% certainty? So this is kind of the tricky thing. Guarantee 100% that you must have been traveling during the time in between when you checked your speed. So if you looked and you were going 20, and then the next time you looked and you were going 40, what is a speed you can 100% guarantee you were going in between those glances? Well, one way to think about this is that when you're using a speedometer, it has to move gradually. It can't jump around. And so because of that, if we started off with a 20 and we know we ended up at 40, I would be comfortable guaranteeing that we must have gone 30 miles per hour at some time in between. Now, the reason for that is because 30 is in between 20 and 40, and a speedometer cannot jump around. So if you're going to go from 20 to 40, you're going to have to pass through all the numbers that are in between. Now, what is one speed that you might have gone in between those two times, but you can't be 100% positive? Well, one thing that I could imagine maybe happened is that you sped up, you got all the way up to 50 miles per hour, and then you slowed down, you let off the gas a little bit. So I might be comfortable saying that, hey, maybe I went 50 miles per hour at some point. But I don't know that for sure. I would actually be comfortable guaranteeing any number that is not between 20 and 40. Now you might have, for example, slowed down for a second, maybe there's some traffic in front of you, you're only going 15 miles per hour, and then sped up when the traffic moved a little bit faster and you're going 40. It's possible to have gone 50 or 15 or any number that's not between 20 and 40. I just wouldn't guarantee it. We don't know for sure. The only thing we know for sure is that to get from 20 to 40, you had to have passed through any number in between. So I could have said 30 here, but I also could have said any number between 20 and 40. And maybe I should make a note of that. I could have picked any number between 20 and 40 and been 100% sure that I reached that value. Now, by contrast, I want you to imagine that you're looking at recent prices of iPhones. You know that an iPhone 11 cost $1,100 in January and that the price is now $900 in June. What is one price that you can 100% guarantee that the iPhone must have cost in March? So we're looking specifically at what's happening in March, which is in between these two values that I know. Now, here's the problem that I'm having with this question. When I look at prices, prices are allowed to jump around. It's very possible that this price was $1,100 in January. It was also $1,100 in February and March and April and May, and all of a sudden they just marked it straight down to $900 in June. So because of that, because prices work a little bit differently than a speedometer, you don't have to necessarily pass through all the numbers in between for a price. They can just mark it down to whatever they want. I would say there is no price I would guarantee because prices can jump around. So maybe just all of a sudden on June 1st, they just marked it down to 900. We don't know. What is one price that the iPhone might have cost in March, but you can't be 100% sure? Literally anything. I would say, hey, it's possible it cost $1,200. I don't know. It's possible it cost $700. I don't know. Anything. But because prices can jump around and we can just randomly change the prices by having a sale, it could be any number. We can't make any guarantees because of that. Now, if we look at these two problems and contrast them, we were able to make certain guarantees about the speedometer problem that we could not apply to the prices problem. And this really illustrates why we can use the intermediate value theorem sometimes, and sometimes the intermediate value theorem does not apply. The thing that made the speedometer more guaranteeable, which I know is not a word, but more guaranteeable, is the fact that it can't jump around. So I could guarantee any number that was in between. Now, I couldn't guarantee the numbers that were not in between the known values that I had, but I could make certain guarantees based on the fact that the speedometer cannot jump around. Because prices can jump around, there were no guarantees that I could make with 100% certainty about the price of these iPhones. So let's take what we just talked about and apply it to a function. When we apply that same reasoning to a function, here's what we can come up with. In the previous examples, we illustrate the main ideas of the intermediate value theorem. The first main idea is that in order to guarantee that a function has certain y values, the function must be continuous. This is why we can make guarantees about the speed of the car, but we cannot make guarantees about iPhone prices. If the values can jump around, then they're not continuous. And if they're not continuous, anything can happen. Also, any value that we guarantee must be between the function values that we know. This is why we could guarantee that we traveled any speed that was between 20 and 40, but we could not guarantee, for example, that we traveled 15 miles per hour. It might have happened, but I wouldn't be willing to guarantee it 100%. So keeping that in mind, that these are the two conditions, let's see what the intermediate value theorem says. The intermediate value theorem is the first of two theorems that we will learn this year that are called existence theorems. This means that the theorem will allow us to guarantee a certain feature of a function exists, but it will not tell us the exact x value where that feature occurs. To connect this to the examples we've already done, think about it as I could promise that I went 30 miles per hour, but I don't know if that was after 5 minutes or after 10 minutes of driving. It just must have happened sometime. So here are the conditions. Now, a function must meet the following criteria before we can apply the theorem. So before you can even think about applying the theorem, you need to check if these things are true. Number one, the function must be continuous on a, b. Now, when we say a, b here, this is an interval of x values. So the function must be continuous between these two x values. Second condition, so we have to have both of these things in order to use the intermediate value theorem. The value k, which is going to be a y value, we want to guarantee. So this would, for example, be the 30 miles per hour in the previous example. The value we want to guarantee must be between the values of the endpoints. I'm going to change my mind here and do this in a different color so that when we're showing our work on our graph, this is going to hopefully help us make some connections. And the y values of the endpoints would be like the 20 miles per hour and the 40 miles per hour that we had in our example. If your function's continuous between your x values and the value you want to guarantee is in between the y values of the endpoints, then the conclusion of the mean value theorem, or the intermediate value theorem, says we can guarantee that there is at least one x value, which is between a and b, the x values of our function that we're guaranteeing is continuous, such that f of c is equal to k. So at that same x value, we have our desired y value. So I personally think that this theorem is easiest to understand if we see it visually. So here's how to visualize this theorem. We're going to be looking at a function on a specific interval. So like we said in the conditions, the function needs to be continuous between a and b. So these x values, the function is definitely continuous from here to here. Now we're also going to be looking at the y values. So let's say, for example, that the y value associated with a is f of a. So on the graph, when you plug in the number a, you get f of a. And the y value associated with b is f of b. So when you plug in the number b, you get f of b. So those are 2 points on the graph. So we know that the function is continuous from this point on the graph to that point on the graph. Now, since our function is continuous, we cannot jump around. That means that no matter how many squiggles you put in here, you have to connect these 2 points. That's what it means for the function to be continuous. Now, if we choose a k value that is in between these two y values, so remember the k value is a y value that's in between these. The intermediate value theorem says that because this function is continuous, there must be a place on the graph where we have a point that has that y value, and we call the x coordinate of that point c. In layman's terms, here's what it means. If you can't jump around, then to go from 20 to 40, you have to pass through 30. It's impossible to get there without crossing through because you can't jump around. You're continuous. Now, how do we recognize that we need to use the IVT? We can recognize that we need to apply the IVT when a problem says that we need to justify our answer. The word justify in calculus often means that we need to use a theorem. And the problem will always ask us, can you guarantee, so can you promise me a specific y value of a function? So can you guarantee me that the function has this output? So can you promise me you had to go 30 miles per hour? Well, yes, because in order to go from 20 to 40, you would have to cross through 30. Now that's going to be the end of this video. In the next video, we're going to go through some practice problems and see some strategies we can use to apply this theorem successfully in the types of problems that you might expect to see on an assessment. So thank you guys so much for watching, and I look forward to seeing you soon.